Welcome to the next video in the systems programming video series. We just finished week 2's work, and so we're moving on to week 3, where we read chapter 3 of the textbook Dive into Systems. This chapter is all about C debugging, I think primarily focused on the possibly most important tool for debugging in C programs, which is GDB, the GNU debugger. We'll also talk about Valgrind and memcheck, also very, very important tools in debugging C programs. Because this is going to really follow, a lot of code, especially code that's good to sort of interactively play with, then rather than try to annotate documents the way I have in previous videos, I'm going to try to just set the textbook next to the code and show the code walkthroughs. Okay, as we get into section 3.1, we're talking about GDB, which you can read an abstract description, but I personally want to, as much as possible, jump into sort of just seeing examples. The conversation in this first section is going to sort of center on this file, which is nicely linked in the online text that you can copy and paste. And so I just went over to this code and select all, copy, and then I made a directory where I'm going to hold the examples that we use in chapter 3. And this thing is supposed to be called bad program or bad prog. So I went and just literally created this file and pasted right into it. And we'll look at that in a minute. I also just, for the sake of, making, kind of following a procedure, or I don't know what, making a makefile. So here is the makefile. To make this file, by the way, just tell you what, let's go ahead and delete this, because it could be nice just to actually watch someone make a makefile, just in case you're not totally familiar with how to do that. So literally all you do is you make a file. It's just a plain text file, and you call it nothing other than capital M makefile, no extension, and that's it. That's how you create your makefile. Now to set it up so that it makes the programs from the source code in the current directory, then we'll call this bad prog, that's the name of a command, separated by, first we're going to say its dependencies, but it's only going to have one dependency, the bad prog.c file. And then you line break tab, and here you give the compiler command. So gcc, what is this? Badprog.c-o badprog. So that'll take the source file, compile it to a binary, and call the binary badprog. So this is all very standard. We might as well go ahead and define the clean function, which is very standard to have in makefiles. It was in the previous assignment, so I'll go ahead and show you in a second what that looks like. In fact, actually, I probably need to remind myself exactly what goes here when you want to define clean. Oh, right, nothing. Okay, because I guess no dependencies. But so if you want to clean, which basically just removes all of the binaries that you have compiled, which is how you do it if you want to just know for sure that you're starting fresh. Basically just deletes everything in the current directory other than the source code, so that, in some sense, you're starting fresh. So the way you do that, this rm is a Linux shell command. So this is for remove. This will remove files. Honestly, in case this is of any interest to anybody, maybe I ought to just go ahead and come over to this directory and show what happens when I call make clean, right? So you say make so that the terminal knows to go look into the make file to look for its instructions. And then you say clean so that it will execute these commands under the clean command. And so when I execute that, it runs exactly the command that was under the clean command name. And so that's what you see right here, right? So it executed this command and it removed snack bar. So there used to be an executable snack bar file here. It's gone now. It removed also password and RPC. And probably, I think what this is saying is that if there are any log files or errors or anything that happened along the way, to pipe them into /dev/null. Not totally sure why you would do that, but I'm sure if we went and looked at this directory and tried to find where any log files were that's related to this, we'd be able to find them. I'm not terribly interested in that right now. I just wanted to demonstrate what happens when you call a clean function, which cleans out all of the binary executables that you may have compiled. So anyway, that's what that does. Very standard to have that, and I am going to give our directory a clean command. For me, that should, at least right now, only mean remove bad prog, because that's the only executable that should get built at any point for now. Yeah, let's say, actually, as soon as I say that, I know that's not actually true, but I'll change this, I'll edit it later when I've made other files. Okay, so let's point the directory back to, what was it, chapter 3? Yep, okay. And ls just to see what files are currently here. Since what I have here, let's come up here, let's save that. Let's come over here. Now this is, again, just the pasted in code from the textbook, and I have not yet compiled it, so let's go ahead and see what happens when I call make bad prog. And so again, right, the make is saying to the terminal to go look in the make file, and I'm giving it the command bad prog, which tells it that what you're supposed to do is execute this command. So let's see what happens when I enter. It does exactly what I thought it should do, right? It executes exactly the commands that I said to execute. And you can now see that the binary executable bad prog is right there as we should expect. Okay, let's go ahead and run bad prog. So bad prog, that's how you run. The max value in the array is 17. Why does it say that? Is it 17? So let's close the makefile and let's look here. So, reading from the top, okay, it includes some libraries. It defines this function find and return max, which the comments here tell us that this should find the largest element in the array, so that must be this array, and return through the max, return it through max. Now that max is presumably that variable right there. You may already detect a bit of an issue here. This is a little weird. So if it seems weird, try not to think about it too much, because we don't want to identify the bug just by looking at the code, right? The point of this whole exercise is to see how GDB will reveal to us the bugs in this code. But so, yeah, like if you've already noticed the bug, which I think I have, let's not say it, let's not admit it to ourselves that we see it, and let's pretend and show how GDB will help us to discover bugs like this when we really need it. It may be worth noticing that what this returns is 0 on success. So presumably what that means is it returns 0 if it successfully encounters or stores the value, the maximum value of the array into this variable. So when that happens, the function returns the value 0. And in the other case, returning 0 is a signal that an error occurred. Now that's just the definition of a function. Down here we have the main, and it's got some argument parameters. We define the this array, a static array. You can visibly see that the max is 60, and since down here in the output it said that the max was 17, that is probably the sign that we need to know that there is an error in this program. We initialize max to the array at coordinate 0. So if it was initialized at 17 and ultimately returns 17, that's maybe some kind of, I shouldn't be thinking about that. I shouldn't be finding the bug in any way just yet. But we do at least need to know something about how this program is intended to run. So it's kind of a funny exercise. But anyway, so we say if this is not 0, which means that there was an error, right? Remember up above it said that it returns 0 if it was a success. So here we're saying if it was not a success, then print an error message and exit with an error code. Otherwise, print the max value and return 0. So I think a lot of that makes sense. But we see that there is a bug, right? It is saying 17 when we can tell that the correct answer is 60. So what is the bug? And this is, right, we're going to use GDB to diagnose this. So let's follow along with the textbook and say, okay, so to get started, we want to compile the program with the -G option. So since I'm still here in the directory where my source code is located, I would like to compile the source code, but this time with the -G option. So I'm going to say, what is it, GCC -G applied to my source code badprog.c. I think that is basically the command. Yeah, that is exactly the command that the book gives. So we're going to execute that command. Now notice that I now have an a.out file, which we don't even want to bother trying to read, but I have this a.out file, and that is the one generated just now by this command. You can tell because I didn't tell it to, make an executable file and give it a name or whatever. I just said compile, and here's the source code. So by default, when, I think we've seen this before, by default, when you do that, it just creates an executable called a.out. Now that may be nice because, like, the thing that I'm right, like this is the executable set up for debugging. That's not the one that you actually want at the end of the day. That's just the one that you're going to run GDB on. So maybe it's good that I have like this as my debugging program and this as the actual program that right now is buggy, but later on I'll come around and fix it once I figure out what the bug is. But it's maybe good to not have them called the same thing or something like that. So anyway, if we want to start using GDB, then we call GDB on the that thing that was compiled with the -G flag. So let's call GDB on a.out. And when we do, we get this right here. By the way, just notice that GDB is a terminal program. So this is, more or less the kind of thing that you're going to see when you start using GDB. It tells you a bunch of information about your computer and about GDB and whatever. And then it says that you can type return for more, I guess, more information, Q to quit, or C to continue without paging, which I take that to mean, don't tell me any more information, just take me to GDB. But I'm going to go ahead and hit return just to see what it looks like. And when I do, you get all of this information. And so, okay, more information, more information, more information. You can check the documentation, which that could be a useful thing. And then type apropos word to search for commands, but then that got cut off. So let's hit return one more time. And so type apropos word to search for commands related to word. So that's a nice, helpful tip, right? If you know of some command, like here, actually, let's just skip to a command break, right? So we're going to use that a whole bunch. That makes a breakpoint, but let's just see what happens if in GDB I type apropos break. And here it gives me a whole bunch of information about break. Let's see. So there's where I typed apropos break, and it says advance, continue the program up to the given location. So it's a little unclear exactly what this is saying. It looks like advance is like yet another command. I guess, okay. I think what it's saying is, this is almost like reading the dictionary. And so break is described here. It's set a breakpoint in a specified location. And it's only showing you this because it's like showing you what is immediately above break and what is immediately below break. I'm not honestly totally clear on why you would show that much surrounding information when what you ask for is break. But I don't know. I guess if one word is sort of like another word, you'd kind of like to see what's around it and just like gain information that way or something like that. Sounds reasonable. No really loud complaints. But what the information that you really want when you ask about break is right here. And I think what it's basically telling you is that you could type break and then after that, specify a location, which is a line number, like, for instance, 36 or something like that. So you would type break and then 36, and that would set the, hit enter, and that sets the breakpoint. But it's saying that, well, but you don't have to type the word all the way out. You could just say BREA, or just this, or just this, or just B. Any of these abbreviations work exactly the same way as typing the word break all the way out. So anyway, that's using apropos. We could type return for more information so we could continue seeing further commands beyond this. We could quit, or we could continue without paging. I think I'm going to continue without paging. Oh, interesting. So, okay. So it did show me the rest of the information, but it did not walk me through it page by page. And it just took me back down to or back to the GDB sort of what would we call this? I guess the GDB terminal or something like that. Anyway, so there we go. That's a little demonstration of using apropos on the break keyword. So now we're going to get into this example, right? So we've already compiled, we've already called GDB. Oh, by the way, one of the first things you want to learn when you learn about how to get into a system is you also want to learn about how to get right back out of the system whenever you want. So that would be quit. So now we're back to the terminal, but I could type this again and hop back into GDB. And then if I just type Q, I'm back out, so then GDB, and then I'm going to say just continue without paging, and there we are. I'm now at the GDB prompt, and okay, but so the point of GDB is to simulate your program, but to do it, either by using breakpoints to pause the program at certain moments, and then once it's paused, you can print out the contents of the variables at this moment of execution. Or you can also call the word next, and it will walk through your program one line at a time, pausing every time, so that at any given moment you can ask it to print the values of variables that are around at that moment. That's basically the outline of what GDB does. We'll see the details of various other commands as well, but they're all some version of that basic story. In order to debug this example, we are going to run GDB. So so here we're in GDB, but we're not yet simulating the bad program, the one that we want it to simulate. So to get it to start simulate, before doing that, I think it wants us to set a breakpoint. Yeah, here, it wants us to set a breakpoint at main. So let's go ahead and set a breakpoint at main. And so when I say break main, what it's doing is literally going up to, through the file, looking for the function named main. It finds it right here and sets a breakpoint right here at line 34 in my implementation. On theirs it said 36, but maybe the code has changed or something like that. In any case, the important thing though is that when I said break at main, it breaks right here. And what you really want to know is that breaking here pauses it right before entering or executing this line of code, right? So at any given, whenever you're setting your breakpoint, just know that when you put a breakpoint on a line, the computer will run up to that line, but does not run that line. It's what the computer is about to run as soon as you move past the breakpoint. Right, so what does it want us to do next? Okay, and now it wants us to run. So, why not? Let's just jump in. And to run, we just, in the GDB prompt, we type run, hit enter, and here we are running. And it, said, okay, so where did I call it? Tell it to run. I told it to run here. It said starting your program, doing some, telling some information. But here's where it's saying I reached breakpoint 1. Breakpoint 1 is on the line with the main function. argc is equal to 1. That makes sense because at this moment in the run of the program, there were no command line arguments, and since the command to execute the program is regarded as one of the command line arguments, then that's the only command line argument, right? So argc equal to 1 makes sense. argv is the the address, I think, of the program itself. Not that we need to know that, but okay, just making some sense of some of the output here. And we're paused on line 34 of the source code. Cool. On line 34, here's what it reads. So you get to see the code. And what do we want to do from here? Well, it's showing you their printout. I'm showing you mine. It's very similar. And what they next want us to do is right here at this moment, just to see what is around. We're going to call list. Now, what did that do? Maybe I want to expand this. But so when I called list, right here, that's where I called list, and it showed me a little bit of the code above the main declaration, right? You can see that up here. This is the source code just above the main declaration, and so you're seeing this part of the source code right here in GDB. It shows you line 34, which is where we currently are paused, and it shows you a little bit of the source code right after line 34. So basically it shows you, right, so when you call list, it shows you a little bit above the current moment and a little bit below the current moment. If we wanted to, we could list other places in the source code. So we could call list find and return max. And this will show us a little bit above and a little bit below the function named this. And so when we do, we see the commented code up here just above the find and return max function. And then we see the full line of the find and return max function and a couple lines just after the find and return max function. So that's what list does, right? Shows you a little bit above and a little bit below either the current moment if you don't specify anything else, or any other place in the source code if you give it a specific place. Here we did it with the name of a function, but you could also do it with a line number. So if we said list, let's just see what happens if we say list 1. And so list 1 shows you the very top of the entire C file. Okay, from here, so keep in mind that where we really are in GDB is we are on line 34 of the main function, meaning that we have not yet stepped into the function. Now, if we call next, as it wants us to do, it's going to start going through the program one line at a time. So if we call next, let's predict what's going to happen, right? If I call next, then it is going to sort of, in some sense, let this line of code execute, which basically just means that the main function is now going to be saved somewhere in the computer's memory, knowing that main refers to the main function, right? That this is like the name of the function, and it's going to know that these variables are going to have whatever bindings, and that, right? So basically, by running this line of code, the computer, in a sense, kind of learns about what the main function is or something. Or, maybe more realistically, it's actually going to start walking through the main function. So it's actually going to start executing. So the next thing, like when we call next, it's going to move to this line, right? It is going to progress to this line and not yet execute, right? Because again, right, whenever you reach a line, it pauses and does not execute that line. But then when you call next again, it'll execute and move on. But at any given moment where you see where you are is a line of code that has not yet executed, but it is the next thing to execute. So, okay, so if we call next, it should show us this line of code indicating that it already processed, right? Like, because we're here and waiting for this line to process. But when we call next, it will process and then show us this line of code indicating that this is the next thing that would get processed if we hit next again. So, okay, hit next. That is exactly what we expect to see. The main function declaration got processed, but we're starting to execute, or we're just before the execution of line 36. Okay, If we call next again, then this line, right, will execute, and it will move us to and pause right before line 38. So let's see that happen, and there it is. And we could, at any given moment, right, now or before or whenever we want, we can print any variable's value that we may choose to print. The max is equal to 0 at this moment. I guess that's interesting. Why would max be 0 when you would think that max doesn't even exist at this moment? Yeah, and if you say foo, then it knows that there's nothing called foo. So it must be aware of the integer max, and it must have initialized it to the value 0 before we were even aware of, anything happening. So, okay, that's interesting. But okay, so we can print max, and max is 0. Okay, we can also print the array at index 3. So let's go ahead and see if we print array at index 3, then it shows us the value in the array at index 3. By the way, these little dollar signs in their code, it says 3 and 4, and in mine it says 1 and 2. Well, that is just tracking which things you have asked to see printed so far. So probably in their code, it says 3 because when they were, playing around with this code and generating it, they, called print on a few other things that I did not before they got around to calling print max. And so that's why they say $3 is it's like the third thing that they printed. But for me, 0 was the first thing that I printed. So. What else could we do in this setting? So we could call next, and that will take us to just before this if condition occurs. That will be after the value of max has been assigned from the array. So that should be the moment when max takes the value 17. So let's go ahead and call next. And okay, we're here. Let's print max and 17. Cool. At this moment, if we were to call next, it would execute this line of code, it would in fact execute this line of code and take us to the next step, which might be inside the if condition, or I think because we know that this does not return an error, then in fact it would take us down here to line 44. But that might be skipping over the source of the bug, right? Because the source of the bug, there's a good chance, is inside the definition of this find and return max function. So we don't want to merely execute this and move right along to, line 41 or 44. Instead, we would like to actually step into the execution of the function and pause inside the execution of the function. But that's not what you get if you call next, so we can't call next. So what do we call instead? If we actually want to step into the call of the function on the current line, what you call is step. And so if we call step, then you can see that this took us to line 21, which is up here because we stepped in. I guess, why did it not take us to line 19? Why did it take us all the way to line 21? Let's see if it's the same for them. Now you could have you could have accomplished the same pausing behavior by inserting a break point before we ever walked through the program. But it's nice to know that you can control this either by setting breakpoints in advance, or you can change your mind in the middle of the walkthrough by, calling next and step and so on. It is a little like, I wonder if maybe it didn't stop at line 19 because there's almost nothing to do at line 19. I wonder if that's it, or does it always just execute the first line and move on to the second one? I'm not sure about that. Maybe we'll sort of discover this behavior as we play with this more and more. But in any case, okay, so I guess at this point we are at line 21. And we could go ahead and list everything that is surrounding line 21, although we see it here, so I'm not sure I want to do that in my little, in the terminal. But we could print the value of array1 at 0 if we wanted to. That's maybe worth just playing along in 17, exactly as it ought to be. Print max 17, exactly as it ought to be. We could list, but we can see the code up here, so I don't want to list right now. And we could call and you can call list again and again and again, and it'll just keep showing you more and more code. So that's a nice way to, like, if you're at any given moment in the, in the debugger, and maybe it's hard to jump around in the source code while you're working in the debugger, then yeah, list is very useful. But if I already see it in the source code right here, I don't necessarily need to list it in the terminal. The next thing that it wants us to do is set a breakpoint at 27. Why set a breakpoint at 27? I guess that's where we actually assign the value of the max variable, or possibly reassign the value of the max variable. And so maybe we're interested in pausing right before this happens to see, because we would like to know that the value 60 gets assigned to the max variable. It should, right? If we're trying to make sure that the max variable absorbs the maximum value in the list, we'd like to see that it eventually takes the value 60 and never loses the value 60. So that's a good reason to set that to be a breakpoint. So what's worth knowing is that even though we're in the middle of a run, we can still set breakpoints. So there it is. We have yet another breakpoint, a second breakpoint, and it tells us the line number 27. And suppose, as we kind of do right now, we're not really interested in simply stepping, or nexting until we eventually get to this line. We want to just let everything run until it hits this breakpoint that we just set. So for that, we type cont for continue. And then it executes until it hits line 27, where the breakpoint is, and it pauses here before executing this line. And that's where we are right now. Now that we're here, it would be nice to see what is the, let's just see everything. Like, what is around here? So we could print max, print I, and we get values that I think all make sense. I was initially 1, so that is why the first time that we hit this breakpoint, the value of I is equal to 1. Max was 17, and because this line has not yet executed, then max should still be 17. And what is the value 1 in the array? So that would be index 1 is 21. So since max, which is 17, is less than array at index 1, this condition has executed. We do reach this. In fact, I guess we reach this line because this condition was satisfied. Otherwise, we would have to wait for the for loop to keep going until eventually this line actually did, execute, basically. So in any case, so what should happen is that immediately after we release the breakpoint, and let the computer run another line, max is going to get overwritten with the value 21. Now, since it's a little obnoxious to keep printing every single thing, making an explicit command to each thing that we want to print, then maybe we would like to just tell GDB all the things that we want to see printed every single time that we tell it to progress, right? And so that's what the display command is for. So we display I, max, and array at bracket I. And I don't know that I can do all of that in a single line, but let's see. Oh, okay, but I can do it when I comma separate. So display I, max, array. Oh, right, and there is no array, there's array 1. Great. So now the next time that I call cont, it should not only release the program, let it execute, max gets overwritten with 21, the for loop increments and comes back around, and we check this if condition again, and the next time that the if condition is satisfied, we will again hit the breakpoint and the program will again pause. So let's go ahead and cont and watch that happen. Oh, I guess when I told it to print I, max, and all that other stuff, that didn't go the way I intended it to go because it's not printing the value of I. So let's go ahead and display I as well. So it's equal to 2, which probably makes sense if we come back down and look at this. Yes, so now max was 21, but on the next go round, right, the next coordinate in the array has value 44, where 21 is less than 44, so that if condition will be satisfied, and therefore we do enter line 27 when I is equal to 2. At this moment, max is 21, the array value is 44, and as soon as we release the program, max will get overwritten with the value 44. And so if we call cont again, we should now see all of that print. So right, so we can see the max print at 44, we can see the array value is 60, and the value of I is 4. Notice that we skipped over I is 3, because when I is 3, the new value that was encountered in the array was actually not bigger than the max value, which was 44 at that moment. So when I was equal to 3, we never got inside the if condition, right? This condition was not satisfied, and so we did not enter this line, and so we never had an opportunity to reach the breakpoint. But then when I incremented one more time and became value of 4, at that point, the value of the array was 60, which now is bigger than max, and that's why we do yet again hit the breakpoint, and that's why it's pausing here. Okay. If we call cont one more time, it'll be interesting. We call cont, and we see that it exited. Now, this is not exactly what happened for them, because for them, they actually, hit the breakpoint again, and saw that I was equal to 5, max was equal to 60, array at I was equal to this very large number. Now, but that's not what happened on my system. My system said that it simply, returned and inferior 1 process exited normally. So I'm honestly not clear on why. What exactly that means, but we could look it up. But I can at least tell you this about why their behavior does not match exactly my behavior, and that's just because what they're encountering and what the program, right? One of the bugs in the program is that we took this up to I less than or equal to len, which means that I was at some moment equal to 5. That's why it's equal to 5 in their display. Now, when I was equal to 5, they accessed array at I and got this number. That is a total accident, right? There's no way you could have predicted this, because since you're going beyond the bounds of the array, you have no idea what's over there. This is why you have to be really careful to never do index out of bounds mistakes in C programming, is it'll let you do it, but when you go over to index I, you have no guarantee about what value is going to be found there. It's some, any random process might have put some kind of, possibly garbage data there that you could never predict. And so on their machine, something happened to cause it to have this value at index 5. And that's why they're, and so this is the, how you could identify the bug. On our end, or at least on my machine, perhaps what happened is that we accessed index 5, right? So also on my machine, we would have hit index I equal to 5, but for whatever reason, whatever garbage data it found on my machine at that location, it might have somewhat magically been less than the value of max at that moment, which was 60. Now, that's fairly surprising. That's probably a somewhat low probability event, but that's my guess about why it didn't hit the breakpoint yet again, because it really should have set I equal to 5 and run all this code. And so if it's not showing me the breakpoint, it must have run this code, but this condition failed, and then the whole program just exited normally. So anyway, so that's why you see their behavior this way and my behavior this way. Well, so it is a somewhat, natural question. If you were working on my machine and encountered this behavior, how would you know that there's a bug, right? I mean, it would almost kind of like look as though everything went successfully, whereas on their machine, they would actually see that I is equal to 5 and that this array value was some completely unexpected value, and And that would help you to identify that, oh, you have an index out of bounds error, right? Because you could come down here and see, like it's saying that this massive value is in the array, but you can see that it's not. And so that's how you could identify in their behavior that there was a bug. But with my behavior here, how could you identify that there was a bug? Well, you know, what you could do is you could have set the breakpoint at 26 instead of 27, and then you know, you would have seen, you know, at every single iteration through the for loop, you would have seen the value of I and the value in the array, and that would have shown you I equal to 5, which is its own, you know, right? You should maybe, you know that I equal to 5 in an array of length 5 should not exist, but it'll also show you a value in the array, right? It'll print a value in the array at index I, which you can visibly see is not there because, you know, like whatever you get at I equal to 5 is almost certainly not going to be one of the values in the array. So anyway, but there it is. That is an error in the code. We have used GDB to identify an error in the code. We'll resolve that error if we simply make that from less than or equal to a strict less than, which is what they identify here. Okay, we can now quit this. Now, we could recompile, and we will find that if we recompile, the bug is still not fixed. It still says 17 even after fixing this issue. So let's do it all over again, basically. Let's recompile, and this time let's go ahead and make bad prog. Oops, make bad prog. Oh, because I didn't save the source file. And then let's recompile the debugger code. So that would be gcc-g applied to, what was it, bad prog.c. And so now this a.out should have been recompiled. And so we can rerun this with a new code. So let's go ahead and say GDB a.out. Takes us through here. Let's continue without paging. Let's set a break at main, just because they do. I'm not sure you would really want to set a break at main, but you know, like let's just use these things and see what happens. So we set a break at main. We set a break at find and return max. We jump in. We have broken at main. We can cont and just let the program run from here until it hits the next breakpoint. And so breakpoint 2 at find and return. So this is at line 21, presumably because you know, we let it run until it got called, and it, I think, just skips over this line and takes us to the first line where some actual manipulations occur. So we're broken at this moment. So we'll go ahead and use the where function or command, and that will tell us, in a sense, where we currently are in the program, especially keeping in mind the execution stack. So we've seen the execution stack before, and it's worth knowing that the execution stack works like a stack in the sense that if you look at these indices, right, the main, the call to main is the first thing that runs. So initially, the main is at stack level 0, which is that's like index 0. But as soon as something new, like the call to find and return max, gets pushed onto the stack, it goes to the top of the stack, meaning that it is now at frame 0, and main is now at frame 1. Right? So when things get pushed to the thing at the top of the stack is the most recent thing, and it's always at frame 0, and everything down from that, the earlier things that were in the stack, they get pushed to higher and higher frame indices. So for that reason, because we are currently in frame 0, which is inside the call to the find and return max function, so that's at frame 0, and main has moved to frame 1. So we get to see that we are in frame 0. If we wanted to, we could move out of frame 0 and into frame 1 so that we could just explore the values of variables out there in that frame at this moment. I'm not sure that's really what we would want to do in debugging this program, but it's a good exercise. It's a good thing to just see that this is possible. So if we call frame 1, this now tells us that we are in frame 1, and we are looking in, right, frame 1 is sort of in the context of the main function with these variable values. And in particular, we're at line 40 of the code. And that's because, kind of we're still somewhat suspended here waiting for the call to find and return max to execute. So that's explaining what you're seeing here. If we wanted to, we could print things that are available in frame 1, like the array. We could print the max, and I think the max here is distinct from the max in the in this context, which is itself actually basically the other bug of this program. But in any case, so we print max down here, and it returns 17, which makes sense. Let's continue. So what does it want us to do next? It wants us to break at line 30. Okay, let's do that. And then continue up to that breakpoint. What was line 30? Line 30 is this right here. So I guess we're letting everything happen in the find and return max function right up until we have the function return. So, okay, we're here. And now we want to print max, right? We want to be down here, print max, 60. Which I guess what that's basically demonstrating to us is that inside of the context of this function, the value of max eventually becomes, and then by the time the for loop terminates, it ends with the value 60 just as it's supposed to, right? So at this moment, right before the call to return, max holds the value 60, which maybe you kind of think is what it's supposed to do. And yet, still, when we get back out to this context, the value of max out here after the call to find and return, if out here the max goes back to the value 17, that's somewhat of an indication of where and what kind of bug you're dealing with. So this shows that the value of max is correctly set to 60 at this moment, and then we can execute the next command. So here, if we call next, that's going to take us out of the find and return function. It'll just return that value and take us back to the context of the main function. So basically it'll let this line execute, and in fact it'll let this whole line execute. We'll see that it's not equal to 0, and therefore we're going to encounter this line. So let's go ahead and do that. So we're going to be paused right before line 44, or okay, I guess actually for some reason, what is that next? I guess we just reached the end of the find and return max function. So okay, so now we call next again, and now we're at line 40. I guess just indicating what? Oh, that okay. So although the find and return function has returned at this point, we still are pausing and hovering on the computation of this condition, basically. And at this moment, it wants us to check where. So what are we seeing when we see where? Right, we're looking at the execution stack, and we can see that the execution stack has now kind of, taken away the call to find and return, and we're back to main being the only thing on the execution stack. So main is again at level 0. Here, now that we're out here, we can print max. We see that max is 17, not the 60 that it was in the earlier execution stack, right back when we were in the context of the function call. And that's telling us what basically went wrong, is that the binding to max in the call to the right in the execution of the function was not the same as the binding to max here outside the execution of the function, which is, just down to the fact that what you really want in your function definition is not an integer, because the integer, this is the whole pass by value issue. This is receiving a copy of the value of max, and then when it's mutating max, it's not actually mutating the same variable as was here. So if you want to fix that, then you would turn this into an int star, write a pointer to an address, and then you'd have to make corresponding issues, like you'd have to deref here, you'd have to deref here, here, I guess, yeah. And then over here, when you pass it in, you would pass in the address rather than the variable. And yeah, and I think that should do everything we need here. So there you go. So I think that should fix the bug. So if we quit and we say yes and we recompile, so that would be make bad prog. Oh, I didn't save the source file after editing. So now make it, now it's new, now /bad prog, and the value is 60, so the bug is fixed, and there we have it. Thank you, GDB, for helping us to debug this program. This has been a long video, so although there's more in this section, I'm going to end it here.